Welcome back, students, to Basics of Mechanical Engineering. We'll continue our syllabus. In the last class, we studied about different types of processes which we commonly look at or experience in the field of thermodynamics. Today, I wanted to talk about the effects or the interactions of these processes or the systems during these processes. There are two types of interactions which we normally consider in thermodynamics: heat interactions and work interactions. To study each of these interactions, we have to understand the concepts of heat and work. To understand heat, we need to understand what is internal energy. So, today, let's have a look at what is internal energy. What is internal energy? Internal energy can be defined as the forms of energy related to the molecular structure of a system and the degree of the molecular activity. All right. So the sum of all of these microscopic forms of energy is called internal energy. The basics of this all, what it implies is that when we have or when we observe any molecule or any substance on a molecular level, that is, we have a microscopic approach, we soon find out that each of these substances are made up of tiny molecules. All right, these are arranged or probably in some they are arranged in some way or form. All right, and each of these arrangements is unique. Now, one common thing with this arrangement is that this arrangement changes as soon as you start heating it up. All right, this arrangement changes as soon as you start heating it up. So, as at a particular temperature, we know that these molecules will start moving, or these molecules have some unique movements. They move in a horizontal manner that they translate with respect to each other. They can even rotate with respect to each other in some limited fashion. All right. Also, they may have some bonds between these atoms. They may have some unique bonds with these atoms. So you will find that each of these motions will carry some sort of finite amount of energy. They will carry some finite amount of energy, and the summation of all of these finite amount of energy, the kinetic energy, the potential energy, the bond energy, the electron the energy within the electron fields, so on and so forth, is called internal energy. Now, internal energy, as I've said, is a sum of all of these kinetic and potential energies. And since it's an energy, it's measured by in the unit of joules. Now, the symbol for internal energy is capital U, and specific internal energy, that is internal energy per unit kg, is of course small u. All right. So what we have learned today, we have learned or we have understood the concept of internal energy. What is internal energy? That is the sum of all microscopic forms of energy: the kinetic energy, the potential energy, the electron energy, the bond energy. All of the sum of all of that is termed as internal energy. Okay, it is denoted by capital U, and if you're talking in terms of specific internal energy, that is the energy contained per unit kg of the substance. It is of course denoted by small u. Now, of course, since it's an energy, we measure internal energy in terms of joules and specific internal energy in terms of joules per kg. We also know that if a system does not do any work interaction, and if you just add energy to it, the internal energy of the system will increase. If your system is an ideal gas, this increases the internal energy, and this internal energy is strictly is the form of kinetic energy in the case of ideal gases. All right. We also know that internal energy is a state function, that it depends on the value of it. It does not depend on how the process or what the process was. All right, so just depends on the final state of the entire system. It does not depend on the process of how it achieved that state. Okay, so this is the introduction of internal energy. I hope this is really clear to you. All right, Next, we have to look at the concept of heat. So what is heat? What is heat? I will give you a moment to think about it. Popularly, heat is defined as the form of energy that is transferred across the boundary by virtue of a temperature difference. So we have a sort of we have an innate understanding of what heat is. We probably know that it is not wise to touch something which has a lot of heat content, right? So but at the same time, talking about heat, it we feel that it is a very abstract concept. So we'll try to simplify it for you. We'll try to ensure that you have a very good understanding of what heat is. Now, to understand how we talk about heat, we have to understand a bit of history about heat. So there was this individual called Carnot, a French engineer called Carnot. Now, as you study thermodynamics a bit further, you'll understand that he was a pretty, or his concepts which he came up with were pretty important. But what when he started talking about heat, what he his idea or his understanding of heat was slightly flawed. So when he talked about heat, he assumed heat to be a physical quantity. So he assumed it to be a physical quantity. It was a sort of a fluid which uh, had no mass. It had no mass, and when you added it to a substance, your temperature would rise. Temperature would rise. All right. So he thought it was a physical fluid which had no mass, and it was very difficult for you to detect its presence. But when you added it to something, the temperature of whatever you're talking about or whatever you added it to, it rose. So as you can see, what he thought it was a sort of a physical fluid. And all of our the way we talk about heat, we talk about heat flow, we talk about adding heat energy to it, or adding heat uh, to a specific object. All of that eventually, results from a flawed, or the flawed beginning of the understanding of heat. So Mr. Carnot, whenever he came up with this understanding, it was a flawed understanding. And when we looked at our concepts further, we realized that, hey, this is not right. Heat is not a physical quantity, so you cannot just add heat to it, or add heat, or it's not a physical liquid that you can pour from one vessel to the other. All right. So what is heat? So heat is nothing but internal energy. So heat is defined as a form of energy that is transferred across a boundary by virtue of a temperature difference. Now, what energy are we talking about? That is nothing but the internal energy. All right. The substances do not contain heat, they contain internal energy. So heat is not a physical quantity. It is just the presence or absence of internal energy. All right. So there's nothing called heat content within a system. Even though we speak about heat content in a system, there is no physical quantity called heat. There is, however, internal energy. So when you talk about heat transfer, what we are actually talking about is the transfer of internal energy from one object to the other, or into a system, or from a system. All right. So this has to be very, very clear within you. First of all, you have to remember what is internal energy. Internal energy is the sum of all microscopic forms of kinetic, potential, and all sorts of these energies. All right. Once you sum it up, you will come across something called internal energy. And what is heat? Heat is nothing but the transfer of internal energy by virtue of its temperature difference. Now, if you think about it, let's again revisit the concept of temperature. Let's again revisit the concept of temperature. If when I talked about temperature, I talked about this crystal lattice. All right. And this is again a very common theme which we have followed throughout the explanation or the exploration of thermodynamics. We have always looked at this crystal lattice for answers. And funnily enough, And what happens is that once you start heating up the substance, when we talked about the temperature, what actually started happening is that, or what we saw that is that this molecule started moving left to right, up and down, side to side, rotated in specific directions. And we defined temperature as basically the average kinetic energy of these molecules. So right. So it stands to reason that when you are adding these kinetic energies, the potential energies, all of these energies, you will end up with some sort of a physical quantity. And this physical quantity is nothing but internal energy. And so if you have something with a temperature difference, what is a temperature difference now? Now, if you remember this concept of what is temperature, and you think about what is temperature difference is nothing but the difference in average kinetic energies of of basically whatever you're to comparing it to. All right. So if you have, say, a substance A which has a higher temperature, and substance B which has a lower temperature, that means obviously it has a low kinetic energy, and you bring it in contact with each other. And what is going to happen is that these physical molecules of A are going to start impacting. They're going moving around, right? So they will start impacting these molecules of B, and they will transfer some of that energy. From A to B. All right. So thus what is happening is that your internal energy is being changed. The value of the internal energy is being changed. So the internal energy content in A is being reduced, and internal energy content of B is increasing. So what is happening right now, from what we see, from what our normal understanding is, we are talking about heat transfer. So what is heat transfer? Heat transfer is nothing but the transfer of this internal energy by virtue of temperature. And what is again temperature? Temperature is nothing but the average kinetic energy of these molecules. I really hope that these concepts are really clear to you. All right. So these are not very elaborate concepts. These have very, very simple definitions, but you have to think about them for a while. All right. So take a moment to understand what I'm talking about. Transfer of heat is nothing but the transfer of internal energy by virtue of its temperature. Okay. All right. What is temperature again? Temperature is nothing but the average kinetic energy of the molecules in question. Okay. I really hope that you have understood the concepts of internal energy, heat, and heat transfer, and why we talk about heat transfer, heat flow, heat content in the way we do. It arose from a faulty understanding of what heat was, and as we progressed and understood what heat actually is, our vocabulary did not change, and that we will find in all the domains of science. You may have a different ways we speak about things, we talk about things, but the fact of the day is that our language skills come in from how we speak and talk about things, but our concepts of science may not reflect the way we speak. All right. So please understand that heat is not a physical entity. There's nothing actually you have to transfer. Heat is nothing but the transfer of internal energy by virtue of temperature difference. All right. Next, what we are going to look at is methods of heat transfer. Now, you must have learned all of this in your earlier years of formal education. But however, we are going to explore each of these concepts in detail today. All right. So again, as we already know, heat transfer is nothing but a transfer of thermal energy, that is internal energy caused by difference in temperature. Its units is same as since it's movement of energy, its units is also that of energy. That is, in the SI units, it is joules or kilojoules or megajoules or whatever form that you are talking about. Now, we primarily have three methods of heat transfer. The first one being conduction, the second one being convection, and the third one being radiation. All right, so let us talk about the three methods of heat transfer and how each of them uh, occur on a molecular level, and how each of them during the transfer of heat in these methods, how each of them will impact the internal energy, that is heat, what we talk as heat content of the system. All right, so first let us look at conduction. What is conduction? So conduction is a method of transfer of heat when you get object A and object B in close, or when you touch them together. So in this fashion, what happens is that the heat is being transferred from A to B, or conversely from B to A. So in conduction, you involve the physical contact of the two objects between which you want to transfer heat. All right, so you need some physical contact for heat transfer through conduction. Okay, I hope I've made myself very clear. Conduction involves, or conduction is the method of heat transfer by means of physical contact. All right, so you need to have, again and again I'm saying this, physical contact between the two objects between which you want to have some amount of heat transfer. Now if you look at it on a microscopic level, you look at it from a microscopic level, what's going to happen is that, let us assume that we have got whatever the composition of A is, it looks something like this. So here in red, you have A. Now this is the edge of A. So the material ends at this particular point. All right. So material end at this particular point. And on the other side, you have B. So you have B on the other side, and I've drawn it in blue to indicate the cooler nature of B. All right. So A is at a higher temperature, A is at a higher temperature, and B is at a lower temperature. All right. So what's going to happen is that now, if you recall our concepts of uh, thermodynamics, the way we talked about heat, what is implied by higher temperature? That the average kinetic energy, of the molecules of A is greater than the average kinetic energy of molecules of B. Now at the interface, what's happening is that each of these molecules are in contact, or are in close proximity to each other. So what happens invariably, as these molecules are vibrating, they invariably collide with the molecules of B. So during this collision, some of the kinetic energy of A is being transferred to the molecules of B. So some of the kinetic energy is actually physically being transferred from A to B, and this transfer is nothing but the transfer of internal energy from A to B. And this transfer of internal energy, by virtue of the temperature difference, is nothing but what we term as heat transfer. Next, let us look at what is, or the method of heat conduction due to convection, or method of heat transfer due to convection. Now, what is convection? Convection is the method of heat transfer due to the movement of fluid itself. Okay, it is the method of heat transfer due to the movement of fluid itself. So let us assume that you have got a hot surface. Here, and you have got a cold surface here. All right, you have a hot surface and a cold surface, and these surfaces are separated by a certain distance, and what is between them is a fluid. Now, a fluid is a general term which encompasses both liquids and gases. All right, so let's assume that there is a fluid in between the hot object and the cold object. Now what is going to happen is that the particles of the fluid are in contact with both the hot surface as well as the cold surface, all right, and they are free to move between this entire system. They're free to move between the entire system. Now what's going to happen is that what is exactly going to happen is that the molecules which are in contact with the hot surface, they will invariably start gaining kinetic energy. They will start to gain internal energy by the virtue of heat conduction, because they are in contact with a hot surface, all right. So they will start absorbing heat. They will start absorbing heat. Okay, so they will absorb some amount of heat. So there's heat transfer taking place from the hot surface to the fluid, all right. So it is the heat transfer which is taking place. Now due to the heat transfer, the kinetic energy of these molecules start changing, so they start moving about. And what's going to happen is that invariably, if they are in a gravity field, that is, if they are in say the Earth's atmosphere or some wherever it is in within the Earth's gravitational field, what's going to happen is that hot things expand, and as soon as they expand, they turn less dense, all right. As soon as they expand, the density is nothing but mass divided by volume. So as soon as they expand, the mass remains the same, but the volume starts increasing, all right. So as soon as the volume start increasing, its density reduces, and what happens is that this causes the hot gases to rise. This causes the hot gases to rise, all right. As soon as that happens, what happens is that the cold gas, the cold or what called cold fluid, whatever is present outside or outside the region which has been heated up, it starts rushing in and it takes the place of the hot gas, all right. So this process, what has happened is that it has taken away some amount of heat and it has moved away. Okay, so it has taken some amount of heat from the hot object and it has moved away, and now there's a fresh supply of cold fluid to take its place and to start this process all over again. Now what's going to happen to the hot fluid? It's going to rise, and probably it's going to come in contact with the cold surface, all right, if there's a cold surface that to give off heat too. Okay, now in this case, the reverse is going to happen. It's going to come in contact with the cold surface. It's going to transfer the heat by virtue of conduction again, and then afterwards it's going to reduce its density. Its density is going to increase. Density is going to increase as hot things expand. Density will decrease, and when things contract, it density increases, all right. Okay, so as soon as the density increases, what happens is that it basically starts falling back down and the process continues, all right. So in this fashion, you are transferring heat from the hot surface to the cold surface, and the method in which it is happening is it's something called convection. Okay, now this method of convection, what we have talked about, is something called natural convection. Okay, so in this case, we are not making the fluid move. We are not making the fluid move in any particular way. We are not forcing it. We are not doing anything. The other alternative is something called forced convection, in which you actively try to push the fluid, cold fluid, onto the hot surface where it can absorb heat and it can transfer the heat from the hot surface to whichever surface you want, or you want to dissipate the amount of heat. Now this is popularly done quite regularly in computers, in motorcycles and other such equipment. So in the case of forced convection, what is happening is that you're forcing the fluid onto it. So for example, you have a fan and you have a hot surface. All right. Now the fan continuously blows this cold fluid onto the hot surface, where it transfers the heat via conduction, and the heat is carried away via convection. All right. So this is an example of something called forced convection. Okay, now in the case of motorcycles, if you all remember the structure of the engine, you have got fins. You have got these fins on the motorcycle. Yes, on the motorcycle engine. And as you move, air is forced into these channels where they transfer heat and the hot gases can escape. So the engine is maintained at a certain temperature or below a certain temperature rather, and prevents any damage. So this is an example of forced convection, where because of the motion of the motorcycle through the air, your air is coming into contact with the motorcycle engine and your heat is being transferred. So this is forced convection. And the other example which we use to explain what is convection, that is term, or that is an example of something called natural convection. All right, I hope this concept is quite clear to you. So in this case as well, when you look at convection, there is some degree of heat transfer due to conduction as well, because you have to conduct heat from the actual object which you want to cool down or heat up uh, to the fluid in question, all right, which is transferring heat. So in this case, this is called as convection, and even in convection you have some degree of conduction. Okay, so next let us look at radiation. So what is radiation? Now, to understand radiation, we have to understand something called electromagnetic spectrum. Electromagnetic spectrum. The electromagnetic spectrum is nothing but the spectrum of or light, or basically it is, you can think of it, what is light? Light is a part of an electromagnetic spectrum. So on one end you have got things like X-rays and gamma rays, and then you have got UV, then you have got light, then you have got infrared, then you have got microwave, then you have got radio waves. All right, so this entire spectrum is called the electromagnetic spectrum. Now this spectrum is generated because of the interactions of the electrical and magnetic fields. All right, and they are transferred from well, whenever you have got this excess amount of energy, it is transferred towards into the environment by means of this electromagnetic spectrum. So normally when you have got some sort of nuclear decay, you'll come across gamma radiation. Whenever you have got some high energy impacts or something like that, you will have X-rays. And then afterwards, when you have got very intense thermal radiation, you will have UV, light and infrared. And normally almost everything will have some amount of infrared. Even we as humans emit this infrared radiation. All right, so we emit this heat infrared radiation, and this is what we can actually feel when you if somebody has a mild fever. You don't have to physically touch the human being. You can sometimes just feel the radiation of the forehead or the arm. And this is also one when we feel, when you don't have to touch something which is hot or cold to find out whether it's hot or cold. Even if you get the hand quite close to it, and you can feel the heat radiating off it. The heat radiating off it is nothing but this electromagnetic radiation in the form of infrared radiation, which is being emanating from this object in question. Okay, then you have got microwave, and a specific application of microwave is in within your kitchen households, where you're using the microwave radiation to basically energize your water molecules, and thus helping the process of cooking. All right, so in this case you're using microwave radiation to actually transfer energy from whatever equipment you have to your object which you want to warm it up. So this is again an example of heat transfer using the electromagnetic radiation. Same thing which happens with radio waves. So you can transfer energy via using this electromagnetic radiation basically using any bits of the electromagnetic radiation. You can use gamma radiation, you can use X-ray radiation, and you can use this the electromagnetic spectrum to heat up whatever object you want to heat up. All right. So I gave you all the example of infrared, which you all do quite on a daily basis. Some of you all may have a microwave at home, and you all have used the microwave to basically transfer heat energy, or try to use that energy to basically excite the molecules of water within the object, and thus raising its internal energy, thus heating it up. All right, so you all have used these different forms of energy to basically transfer energy. So this is something called the method of heat transfer is the radiative method of heat transfer. All right, so at the end of this session, what you all have studied is what is internal energy, its relation with heat energy. Then you have talked about different methods of heat transfer, and also before all of this, we also talked about the historical baggage of the language which we use to describe heat transfer. Then we talked about what is heat, and we talked about methods of heat transfer. We looked at conduction, we looked at convection, and then we also looked at radiation. Okay, then what we have to talk about is, when we talk about all of this, when we try to use this to analyze a system, we have to unfortunately assign it numbers. Now, as we already know that we use them, since we are talking about transfer of internal energy by virtue of temperature, we are using the method, we are using the unit of joules, or joules per kg, in case you're talking about specific values. All right, so when you transfer heat to an object, when you transfer heat to an object or to a system, we say I'm heating up this bottle of water. So in that case, we assign it a positive value. So when you are heating an object up, when you're adding heat to an object, you have to consider it to be a positive value. Similarly, or conversely, if you take away heat from an object, if you take away heat from something, for whatever system that you're analyzing, you have to talk about, or you have to assign it the amount of heat which you have taken out, a negative value. All right, so heat addition is positive, heat removal or heat loss is negative. I hope that you all have understood this concept which I've covered in this class today. All right, that's it. Thank you very much.